All right. Good afternoon. Let me.
Hi, Doctor. Can
Hi,
I have
Professor.
permission to record, please?
Yeah, sure. I will give.
Thank you.
This is William. Thank you.
Yeah, I will give the admission to everybody. Give me a second.
Professor, can I have permission to record too as well? Thanks.
Sure. So I think I gave permission to everybody to record at this time. If anyone doesn't seem to have it, let me know. I will give.
Professor, it seems I don't have the permission yet. It's mine.
My.
Yeah.
All right. You
I
should
also don't have it. This is William.
really. Are you William? Right, William, you have the permission. Anyone else? It seems we have 30 people in class, and the only one I missed is Chris Tucker. It's not yet. All right, let me do this slides. All right. Hopefully, Sahil will join us soon. Right, we talked about polar coordinates, and basically we have shown that in polar coordinates, generally speaking, the equation of compatibility and this is coming in. This is Chris. Okay, I have everybody in. Good afternoon, Chris. Okay, let us start the work here. We have previously shown you guys that this is the elasticity equation that you need to satisfy for any two-dimensional problem, plane stress or plane strain condition in when there is no body forces involved, of course. And phi would be the polar equivalence of the Airy function that in previous equations we have shown how this P function will be defined. So stresses sigma r, sigma theta, tau r theta are defined in terms of the Airy function in polar coordinate system. If this is, if the stresses are defined in that fashion, then the equilibrium equation are automatically satisfied. And the only equation that you need to satisfy is this compatibility equation. And therefore, any solution to that compatibility equation would give you the Airy function phi, from which you can calculate stresses. And we have worked out, once the stresses are calculated, how to define the strain in terms of displacement, the Hooke's law. And we came to a specific case where we have a symmetrical situation. That is to say, the body is symmetric and the loading is symmetric. As an example of that was a pressure vessel, a cylindrical pressure vessel, which is under internal or external pressure. That would be an example of a full symmetry. About the axis of the symmetry, which is z-axis, it presents a two-dimensional problem and is fully symmetric. As such, if it is fully symmetric, this Airy function here would not be a function of theta, so these terms, derivative with theta would cancel out, and we end up with a simpler equation. Once it's expanded, then we come up to this a differential equation. It's no longer a partial differential, it's a simple differential equation. So any problem with a symmetrical situation, plane stress problem, plane strain problem with symmetry, would have a solution according to that differential equation. This is a linear differential equation, and it can be solved by assuming r equal to exponential into power t, and then the general solution is given as a function of these a, b, c, d constants. So we match these constants so that the equilibrium equation will be satisfied. We notice that the stresses are given as a function of these constants a and b and c, and d do not appear in this equation. So presence of the d is of no significance because it doesn't affect your stresses. So we can ignore it. And once the stresses are defined, once these are defined, that's the general solution for any symmetric problem. A special case would be that B is equal to 0. And we talk about that later on, that YB should be equal to 0 in that specific type of problem, and work through the differential, through these equations, assume a cylinder with internal and external pressure, and therefore satisfying the boundary condition here for this cylinder, we will have at the boundary here or there, the stresses are tau r theta and sigma r. Similarly, on that surface, we have a similar situation. The solution for us, the symmetric solution for us, identified that the shear stress everywhere is 0, so there is no shear stress. So the only thing that we need to satisfy is the sigma r. That should balance by the pressure that is applied externally on that cylinder or internally for the other elements. From this consideration, stress at radius A is equal to minus internal pressure, stress at radius B is equal to the external pressure. We calculate A and C here. Substituting these values into the stresses, obviously we get the stress in radial and tangential direction. This is a true solution for a cylinder with internal and external pressure. It doesn't need to be a thin cylinder, as we have the case with the ordinary elementary solution for the thin cylinders that we learned in mechanics of material. As we have indicated, the maximum stress occurs on the inner surface. And that's another formulation that gives you the stress if it is not, if the hole is not concentric. Then we move through these strain equations to calculate the displacement. And the overall solution is better explained in this chart, where the radial and hoop stress, sigma r is radial and sigma theta is hoop stress, are defined based on the dimensions of this cylinder and also internal and external pressure. And identically, the radial displacement is defined. What would be the tangential or the hoops deformation? What is the and what is U theta? What do you think the value of U theta? Let me ask Alex Penaloza. Alex, what do you think displacement in transverse direction U theta would be in this case?
I'm not sure, Professor.
Think about it. Consider the problem is symmetric, right? The load is symmetric about that center. And the pressure is symmetric. All the pressure and the geometry is symmetric. So UR is the displacement that we have in radial direction. So that point would move to this position. And that point could move to this position, and every point along would have a similar UR as shown here. That you can see is independent of theta, right? It is independent of the angle. That is, everywhere here UR is the same, right? Now, Alex, is this displacement symmetric? Apparently so, right? Because we have everything moving to a same distance, and we end up with another circle, which has a symmetric geometry after deformation. Now, suppose if I have U theta, suppose this point in theta direction, that means if this is radial, theta direction would be normal to that. So this point moves to that location. Because we have shown nothing is a function of theta, right? Every other point should move to the same direction. I'm sorry. So this is u theta, that is u theta, that is u theta, that is u theta. All of them are the same u theta, right? Because nothing is a function of theta, therefore every point has a movement similar to what I have shown. What does it reflect? It seems if you do that sort of a displacement, it seems that every point is rotated by some angle. And that would be just like that I am rotating this cylinder about its center by a certain angle. And that does not produce any stress or any strain in the system. That is just simply a rigid body motion. So we cannot have transverse deformation of any form based on the symmetry of the problem and based on the fact that we are preventing the rigid body motion of the object. The stresses variation are shown here in this picture. I talked about that before. And then we came to the specific case of a pure bending. This is just like the previous problem, right? Except a full circle, we have an angle, a segment of that circle. It is like that we have a segment of a circle. So the same solution that we arrived at before can be used here, as we talked about before. So this general solution here can be used for the curve beam where it is exposed to a bending moment. However, in this case, I keep B. I do not discard B. So what are the boundary conditions for this? Any solution you get, you have to check it whether it does satisfy the boundary condition. Otherwise, that's not the solution of your problem. On the upper surface and the bottom surface, there is no stress. So if I look onto an element here or element here, sigma r should be equal to 0 on these surfaces. At r equal to a or at r equal to b, sigma r is equal to 0. I don't need to worry about tau r theta because we have shown for the symmetric problem, this is always 0 anywhere on the material. So on this surface, we have to show only that sigma r is equal to 0. At the noise, I wonder that if somebody lost the internet tries to come in. Oh, that's okay. So that's the first thing. On the top and the bottom, sigma r is equal to 0. That's the first condition. Then on this surface and on that surface, just symmetric, equal when the moment is applied, I should see for each element sigma theta here, and similarly tau r theta, but tau r theta, I just put it there, is equal to 0, as we said before. So on this surface and on that surface, I should show, I cannot say, by the way, that sigma theta is 0, because there is no load applied here. I cannot say generally sigma theta is equal to 0, but I should say that sum of all these sigma theta times their effective area should produce no load, no axial load here. So F should be equal to 0. That means sigma theta dA should be equal to 0. And also the moment of these stresses should be equal to 0. It should be equal, I am sorry, the moment of these stresses should be equal to the moment applied M. This is similar to the case of a straight beam that we discussed before. So we write that equation. Remember that when we are talking of area here, the thickness here, either assumed to be constant T, or you can assume it is 1. It doesn't matter. It cancels out on the equations. So the element of the area on the cross section will be only here. And RdR sigma theta will give you the moment. Make that equal to M, make this equal to 0. And tau theta, we know that already everywhere else is. Working through this boundary condition, substituting for the sigma theta from the solution that we obtained before. Sigma theta, substitute that value. We can calculate the constants A, B, and C. This is the way we introduce the stresses. And we want to show that sigma r is equal to 0 on the upper and lower surfaces. And these are the two equations we derived from that. And also the sum of the stresses in cross sections is equal to the moment. You can just substitute. One way to solve that, you can substitute sigma theta from this equation, put it here, and carry out the integration. You know, it's this expression, get the integration with respect to r, and work it out. It shouldn't be that difficult, but our textbook, Mr. Timoshenko, tried to work it in another fashion. Instead of sigma theta, we express it in terms of the Airy function. Sigma theta, we know that it's derivative of phi with respect to r twice. So let us get that integration. Derivative of phi, second derivative of phi with respect to r. You can make this as A and R as B, and carry out the integration. I don't know if you remember from calculus, AdV or AdX would be equal to the, I'm sorry, I missed one thing. From algebra or calculus, we know A times B dx. If you have such a product, it would be AB minus integral B dx. Something like this. So we do that separation. So integral of A R dr would be integral of the whole thing from B to A minus integral of d phi over dr with respect to R. That's the way it is shown in your textbook. I rather use straight d here instead of the partial derivative because phi is only a function of R, nothing else. So it's better to show it as d there, but that's the way your text is presented. Simplify that, you end up with this, and that notice that 1r d phi with respect to dr is equal to sigma r equal to 0 at the two ends of the curve phi. We know that the boundary condition at the two ends was such that some of the forces here should be 0. So the first term is equal to 0. And the second term should be equal to the moment here. So the area function from A to B is equal to M. Substitute that one there. You will be able to have three equations. A and B and C can be calculated from these three equations. By the way, this method that is given in your textbook by Mr. Timoshenko has some value of, interest challenging you with the calculus of the phi function. But to me, it was easier directly to substitute sigma theta from that equation and carry out the integration. We didn't need all that complication. But it's all math work. At the end of the day, we have three equations. One is this, two equations here, three unknowns. We solve for the three unknowns, and eventually we get the constants A, B, and A and C. Calculate A, B, and C are calculated. Substitute that into equations of the stress. Eventually, the solution are given by these equations. And as we have shown here, where n is given by that expression, which is some parametric equations of the A and B and inner and outer radii of the curve B. We have shown you this table the other day, that comparison of this result that we just formulated here with that which you would see usually in elementary mechanics of material, and see what's the differences. First, you consider First, you consider the formulas that for a straight beam. Sigma is equal to MC, where the half the thickness of the beam over L, over I, moment of inertia. if you rearrange it for the geometry of the beam that we have, the thickness here of a curved beam, if this is B and the other one is A, B minus A is the thickness. And moment of inertia would be given 12 thickness cube. And simplifying that, you end up with this expression where I can consider this constant 6a over b minus a squared as the parameter n. So in straight beam theory, my equation simply becomes m times bending moment over a squared of the inner radius. We had formulation for the curved beam, which assume hyperbolic stress distribution in one of the previous courses you had in mechanics of material, or perhaps stress analysis as we had. And in that case, distribution of the stress is shown to be following a hyperbolic format. And if you look into the hyperbolic distribution, again, that stress could be expressed as the same factor m times m over a squared. That m here would be different than m here, but it would be some m prime times m over a squared. And for the solution we get from theory of elasticity would be also some factor m double prime times m over a squared. So moment over a squared would be common for all of these solution. M values would vary. So I am calculating m values for the straight beam, for the curved beam with the hyperbolic assumption and the true theory of elasticity. And you can see if you compare the linear stress distribution, the straight beam theory, there is a, even with the small ratio of B over A equal to unity, still there is a noticeable difference between the linear stress theory and the hyperbolic stress distribution. As B over A increases, the variation from the linear would be significant. This assume maximum stress 1.5 times m squared over a squared, for example, and this one assuming at least 70-80% larger than the other. But if we consider, if we compare exact solution, we don't see that much of a difference, even in the case of B over A is equal to 3. For example, maximum 2.3 almost, and here is 2.28, 2.28, 2.29. And it's not even 2.28, 2.285, 2.20. Right? So difference would be 0.007 or something. It's fairly negligible. Of course, if we go to a higher ratio, the difference would be larger. If B over A is, for example, 10, you would see a much larger case. That is the case when we have a a very if this is B and there's such a beam like this, where B is much larger than A. In this case, of course, the elementary theory, this one, would be far from the actual results. But for common geometries, for common design that we have. For example, if you want to design a hook, which is sort of a curved beam, usually hyperbolic stress distribution solution would be accurate. And the advantage, as I mentioned before, of the elementary theory is that this formula here is given for any cross section. So you can calculate stress for any cross section, but this solution we have only for a thin rectangular solution. Being close for this specific case, it gives us some assurance that generally speaking, the solution that we have for from hyperbolic stress distribution should not be that different. Joseph was out and now he's back in. Joseph, you're back and hopefully you didn't lose that much. No, this exactly shows the theory of elasticity and strength of material. Variation is very small. One of the things to note, though, is that the radial stress, sigma r, is always positive. And the maximum stress does not occur on the neutral axis, but rather at certain distance from the center. So if you look into that diagram, this is the central point, and it is not occurring at the center, it occurs somewhere to the left. And the other thing which is noted here, maximum radial stress does not occur at the neutral axis, where the transverse load sigma theta is 0. Now, for the case of straight beam, that we have seen also with elementary theory of hyperbolic format. For a straight beam, we know that the maximum normal stress are on the outer and lower bound, one maximum, one positive, one negative, such as this. And on the neutral axis, we have a 0 stress. But that is not the case with the curved beam. With the curved beam, as we know, neutral axis has some eccentricity with respect to the central axis. So the central axis wouldn't coincide with the neutral axis. The next thing that I would like to do here now is to calculate displacement. I'm working through this example, but I would like you guys get involved there and do similar thing for other problems where the stresses are defined and you want to calculate displacement. We begin with definition of the strain in polar coordinate system. Epsilon r, the partial derivative of u with respect to r, and epsilon theta is u over r plus partial derivative of v with respect to theta divided by r. So that's the way we define epsilon theta and epsilon. And in addition, we know that the shear strain is related to the displacement u and v, and we gave the formulas for that. But in this case, in this problem, shear stress is 0. Let me bring Joseph again. It seems he has a fluctuating internet. All right. And I'm not just looking into that beam with the bending moment we applied. I am trying to get the displacement in a general case. for any problem with axis symmetric, not only limited to the pressure vessels, cylindrical pressure vessels, or the case of the curved beam with the moment at the ends. So these are the general equations, sigma theta and sigma r. Let us substitute into the values there and correlate the strain to the stress accordingly due to the Hooke's law. Substitute there, you end up with this equation. Integrate that equation. This is u, the radial displacement, which is given as a function of r because it is a axisymmetric problem. It doesn't have theta in it. Integral of that with respect to r gives you the u in German, plus a function of theta, because we are integrating with respect to r, we get a function of theta. Substitute the value of u into this equation, and we know that this is epsilon theta, so you have value of sigma theta, sigma r. Again, similarly substituted here, and value of u you can substitute from here, and eventually you get delta v over r is equal to 4br over e minus f of theta. Now integrate that expression, we end up with this equation. So we have two variables, f1 and f, that f is a function of theta, f1 is a function of r, that needs to be calculated. Now, to calculate those, we know that the shear strain, or theta, is given by this expression as a function of u and v in polar coordinate system. And because shear strain is 0, this expression should be 0. So substitute v and u onto this equation and make it equal to 0. You end up with these two equations. You can see b would cancels out, and you end up with this equation, which has the term of Joseph. Again, losing the internet and coming back. So we will have this expression that has some terms which has r in it, differential of f1 with respect to r minus f1 with respect to r, and also expressions that has only theta. Separate them from each other. For these to be equal to 0, the expression with respect to r should be 0, and expression with respect to theta should be 0. We make it as such, and we end up with these two differential equations. The solution of that is given by these two expressions. Solution of f1r is fr. Solution of f theta is given by this. Substitute there. You end up with this two equation that gives you the displacement in radial and in theta direction. Of course, we have the constant k, h, and f that needs to be solved based on the boundary condition. Now, Chris was out and coming back. Now let us look into this specific solution for our curved beam. What are the displacement boundary condition for my problem? How do I solve displacement boundary condition? What do I mean by that? What do I need to satisfy to calculate these constants f, h, and k what should I be looking here in this problem? I satisfied, by the way, the boundary condition based on the loads applied. So I don't have a problem with that. What else I need to do to get the constants in displacement? I would like you guys to think about it. Again, Joseph is trying to. So basically, once we solve the displacement, usually you come up with few constants when you do the integration. And these constants should be calculated based on fixing the object of your interest so that you prevent the free body motion of or rigid body displacement. This beam is placed as such. It should not just translate to the right and left. It should not move up and down. It should not rotate. We have those constants can be calculated by fixing it against the rigid body motion. So what should I be doing here? Again, it seems that every ring that it comes here, it seems somebody is losing internet. And once ringing back again, it seems that they are coming back. So the first thing, we consider the center of the beam here. And we say that point is fixed. That means it doesn't move in U direction or the V direction. It doesn't move in U direction. U is the radial direction and V is transverse direction. So we fix that midpoint here against translation in vertical and horizontal, or in tangential and radial direction. That would prevent the translation of that beam, but also we want to prevent it to rotate about that point, right? This curved beam should not be rotating about that point. So how do I fix it? I consider an element in radial direction, such as this element, and say the slope of that should be 0. That is to say, derivative of V with respect to R should be equal to 0. I cannot add additional point here. For example, let's say this point is fixed. You may try that and you may not arrive at a similar solution. So we fix that point there and we say an element in the vicinity of that point, a very close point in that vicinity, should not move in V direction. That means derivative of V with respect to R should be 0. Satisfy these three, we will end up with 3 equations, and we can calculate the 3 constants here. K becomes 0, F becomes 0, and H becomes 0. I'm sorry, the K has this term, right? This is equal to 0. This equal to 0. And that equal to 0. From these two, you can see F and H is equal to 0. but k would have a value here. We need to see what is that a here. But before looking into that, let us, once we substitute that, this is the equation that is left, which has the constant b and the constant k here. Constant b comes from the stress analysis. The constant k is from the displacement analysis. First of all, in this solution that we arrived, we notice for any cross-section, at any cross-section such as the one I show here, let me do a bit of drawing here. Incorrect pen. Which is, say, at an angle, this angle theta, say theta 1 or theta 0, from the center. If we consider this line AB, what happens after the bending moment is applied? What happens after the bending moment is applied and the beam is deformed? Any tangential or the transverse displacement, such as the one I am showing here, V, is calculated from that equation. And you can see that V is made of two parts. One is this, one of that value. The second value for theta equal to 0, k sine theta 0 would be the same. Let me bring this down. So the second term shows every point here moves to the same distance that is translated to the same distance. So that line comes parallel to itself, to a new position. After the load is applied, that line AB moves parallel to itself to a new position, A prime, B prime. And that's what the second term will tell you. The first term shows that displacement would be proportional to R. So that point B, which is closer to point O and has a smaller R, would have a smaller deformation, and point A, which is further away from that, would have a larger deformation. But rotation will be linear with respect to R. Therefore, let me clear the picture here and redraw these. Therefore, any cross-section, such as this one, will move to a new position according to the second term, parallel to itself, and according to the first term, will rotate to a certain degree. In either of these cases, when you add these two cases, it would be that this cross-section has moved to a new position, such as this one. That means the plane cross-section remain plane. That's all I am trying to say here. And that is exactly what we assumed with elementary theory of the curved beam when we formulated the problem, at that time. Of elasticity, or the true solution based on a theory of elasticity proves the same thing here. That is to say, this cross-section is not bulging or it's not deforming. It would remain plane. That's one thing to notice. One thing to note, though, if you look into the expression for the V, it has a term of theta here. That theta is not a single valued function. So remember that when we considered the cylinder pressure vessel, and in formulation of that problem, I assume the constant B is equal to 0 without giving you the reason there. Here you can see why B should be 0. Because that expression would give you a multi displacement. So if I get the displacement here for theta equal to 0 from that expression, I have this term, which is 0. I get a 0 displacement here. When I turn 360 degrees and theta becomes 2 pi, sine 2 pi is 0 again, but this term for B R 2 pi over E is no longer 0. So at the same point on the same cylinder, I should be predicting by this equation different values. It is not possible. Therefore, B should be equal to 0 for the full cylinder. That's why we assume B is equal to 0. So we realize that is some basic thing that we discover at this time, that boundary condition will satisfy constants of integration for the stress will be calculated. But for the symmetrical problems such as this one, those boundary conditions would not be sufficient to solve for all the constants. We have to also prove that the displacement that we obtain is not a multi-value displacement. If there is a term which has a multi-value or produces multi-valued displacement, we should make it equal to 0. So this is additional thing that we have to insert into our solution. Of course, if we are dealing with a segment of that beam, of that cylindrical pressure vessel, which would be the case of a curved beam, such as this one, then I don't have that problem because my theta is only changing from theta 1 to theta 2. It doesn't turn 360 degrees, as is the case with the full circle. So in this problem, I can have beta. And of interest to better understand that value of B, Let us consider, as shown in the bottom, a ring which has a cutout at the point. You have a full ring, and perhaps you cut it with a saw, and you have a small gap in between. Now let us bring the two ends together and weld them together. As a result of it, if that small angle alpha exists before the two ends are being brought together, you will have a sort of a transverse displacement V here, which would be equal to R times alpha, the radius of the ring, average radius of the ring times alpha. Equate that with the equation here. B can be calculated. And substitute back into equations that we developed. You can see what would be the moment required to bring back the moment that is required to bring the two ends of this ring together and weld it. As an exercise, I've written in the bottom, prove this, that this moment would be the one required to bring it back from the equations that we have. And it's a simple thing here. We have already calculated B, which is given by this expression. And just to relax you from this homework, I put the results here. B is given by this equation from previous analysis of that curved beam. And it should be equal to alpha E over 8 pi. From there, you calculate P. Yeah. The next problem I would like to address here is the case of rotating disk, which is a flywheel. It's a very practical problem. A turbine, a flat flywheel that is rotating at a very high speed. As a result of it, we generate inertia forces. So every point would have a acceleration for a rotating disk. One thing you learn from dynamics, which has a velocity acceleration in a normal direction equal to V square over R. So if I have a disk which is rotating with the angular velocity omega, every point such as the point A at the distance R from the center would have a velocity equal to R omega, and would have a normal component of acceleration, AN, which is equal to V squared over the radius of curvature at that point. Substitute V from that equation to here. You end up with this simple relationship that the normal component of acceleration is equal to R omega squared. mass times acceleration, that is density times volume is mass, times acceleration, that gives you the centrifugal force that is created as a result of rotation of that disk. In our elasticity formulation, this is the equation of equilibrium. These two are equations of equilibrium, where R and S are body forces per unit volume. So if this is the total force per unit volume, I just divide it by the volume, and I get rho R omega squared. So your R here is rho R omega squared. So for the rotating disk, S is equal to 0. I don't have transverse loading due to inertia. I only have a radial loading. I will have had transverse loading if we were studying the case of accelerating disk. If it had omega as well as alpha angular acceleration, then we would have had some S here. But at this moment, we are assuming a disk rotating at a constant velocity. So the equations of equilibrium are modified by this term. And because it is a symmetric problem, nothing should be a function of theta. So in this expression, everything which is given as a function of theta, we can ignore it. And simply we end up with the case that, first of all, tau r theta equal to 0 because of symmetry, so that doesn't exist. And this term doesn't exist because derivative, nothing is a function of theta, so derivative with respect to theta equal to 0. The second term, second equation is automatically satisfied. That is 0. So I end up with this simple equation. Derivative of r sigma r dr minus sigma theta plus rho r omega squared is equal to 0. What I did here, this is the equation that we have, right? And that is 0. So it is basically sigma r over dr plus sigma r over r. So derivative of sigma r with respect to r plus sigma r with this over r, that is this term here. And we say this is equal to d over dr r sigma r. So we replace it with this expression. So if you wonder where did we arrive at that solution, otherwise it's the same equation. So this is the equilibrium equation for a rotating disk. That's the only equation. The other one is automatically satisfied. And displacement also of that rotating disk would be symmetric. So radial displacement and transverse direction u and v will not be a function of theta. So for every point, we will have the same u and v here. And if nothing is a function of r and theta, epsilon r and epsilon theta are defined in this fashion. Using the Hooke's law, we can correlate the strain to the stress. And for the strain, we substitute the displacement. Substitute these stresses into the equilibrium equation. We get that equation that defines the equilibrium in terms of displacement. So what am I trying to do here for this particular problem is, instead of working on the problem by satisfying equilibrium equations and compatibility equations in terms of stresses, I express the equilibrium equations in terms of displacement, and the solution here that we get for u and v does not need we don't need to worry about the compatibility equation, because as we have indicated many times, if we work with the displacement and then from displacement we calculate the stresses, the compatibility equation is automatically satisfied. And therefore, this is the only equation that needs to be satisfied to get the solution for that rotating disk. This differential equation solution is given here, where C, C1 are constants of integration that needs to be calculated. Now, from this equation, once u is known, I can substitute back again into this equation and calculate sigma r and sigma theta. That will be the results. Considering the boundary condition at r equal to b, sigma r is equal to 0. For the let me draw the picture. If this is my disk, at this location, on the boundary of this, considering an element here, there is nothing outside, so sigma r at r equal to b should be equal to 0. So that would be one equation. But if it is a solid disk as shown here, at the center, where r equal to 0, I should not have an infinite stress. So this is the equation that gives the stress here. And at r equal to 0, if C1 has certain value, it gives you stress at the center of the disk infinity, and that cannot be the case. It's an incorrect solution. So C1 should be equal to 0 for the full disk. And from this, the constant C is calculated, substitute there. The stresses are defined for rotating disk by these two equations. You can see the maximum stress occurs at the center of the disk, and in that location, sigma r is equal to sigma theta, and given by that equation. If instead of a solid disk we consider a hollow disk. Now the constant C and C1 can be calculated by assuming that there is no stress on this boundary and inner boundary and outer boundary, and these will be the stresses calculated for a hollow cylinder disk with the rotating disk. And you can see the maximum stress is defined as given here. One thing, the last point I would like to make here, one thing to notice is that if we have extremely small hole here, almost zero radius, the solution here with a full disk without any hole would not be equivalent. You can see stress at that location would be twice the stress on the full disk here. And in fact, that would be the stress concentration due to the presence of a very small hole in the disk. I would like to stop here, and I encourage you to work on the next homework problem, and let us see what you have. If you have any question, please join me in during the office hour in an hour and a half from now, and otherwise you're free to go. Take care. Bye-bye.